So today we continue with the integrals. So we started talking about integrals last time. And today we will go on continuing to discuss integrals and their main applications. We also will talk about definite integrals. So last time we talked only about definite integrals, but we will see what it is. Okay, so let's talk about the integral. So if you have a function f that is continuous, then the definite integral is going to be this limit. So, okay, so this is a definition which is not used, so it's very, very rarely used ever. And of course, we're not going to use it. Okay, so nonetheless, so this is how the integral is defined. So you have so you split your interval into small sub-intervals of equal width or equal length, if you talk about the interval, right? So, and then you choose a point from each interval, and then you take the sum. So xi star is a point from an interval, and then you multiply this point by the length of the subinterval, right, which is the same everywhere. And as you take the length smaller and smaller, so you take the limit, and this is your integral. Now, of course, to show it properly, we would need. Okay, I forgot. I think I forgot to share screen, right? Okay, right. So this is the definition I was talking about all this time. That's right. Yeah, you can write your student number into the chat to mark your presence. Okay, so now this is practically never done. So you never compute the integrals with the definition. So here they have an example. They have an example here, but okay, so we're not going to go through it. So let's now go back and talk about the interpretation of this definition and how this definition came to be. So imagine that you have a function, that you have a non-negative function so from 0 to 2, let's say in this case, and you want to compute the area below the graph of the function. So you want to compute the green area on this picture. So how can you do this with the calculus? First of all, of course, to do it properly, we would need to define the area. But okay, so of course, the area is defined that you take approximations. So you fill the figure by smaller rectangles, smaller and smaller rectangles, and then the limit is going to be your area. But we're not discussing it in detail. So okay, we're not discussing here what is area, what's the definition of the area. Now, what you can do, you can split your interval into small subintervals. So in this case, they have 4 subintervals, and then in this case, so you take the rectangles, and okay, so the width of the rectangle is so the length is the length of the subinterval, but the height is going to be the highest point of the function of this subinterval, right? So since the function here is increasing, you can see that on this picture, the height is always value function at the rightmost point, right? So for example, at the height of this third rectangle is going to be here, right? Now, and what you can see that, first of all, you can see 2 things immediately, that those rectangles contain our figure, right? So this is, I think you can see immediately, it's trivial. This is one thing. And the second, that for rectangles, you can actually compute their area, right? Because, okay, for rectangles, you just know what is the area. It's the product of width by or length by height, right? Or width by height. So in this case, this is what is going to be the area, right? So it's going to be it's going to be 1/2, right? For example, 1/2 times f of 1/2, because this is the area of the first rectangle here. So 1/2 is the width. This 1/2. So it's horizontal dimension, and then f of 1/2 is going to be the vertical dimension, because this is the height, right? And the height is f of 1/2. And the same for the other 4 rectangles. So the height of the last is f of 2. So this is what you get. And this is an upper bound, right? So this is not the area that we are looking for, but this is an upper bound. Now, in the similar fashion, we can take the lower bound, right? So this time, we take the height of rectangles to be the lowest value of the function on this interval. And since the function is increasing, then the lowest value is going to be the leftmost thing, the leftmost value of the function, right? So the value of the function at the leftmost point. Okay, and so here is the same expression. This is our leftmost this is our leftmost okay, so this is the sum of areas of those rectangles, with the height being the value function of the leftmost points of the intervals, subintervals, right? So here we have the same expression, or similar expression as we had here, but the difference is that, of course, here we have f of 0 instead of f1/2, and so on, right? So you kind of shift to 1/2 to the left the value under f. So okay, and this is what you get here. You compute it, and this is what you get. So recall that f is a given function, right? So f is here is this function. So f is just a given function, but it doesn't matter. At the moment, it doesn't matter the exact form, but let's say it is this function. All right. Okay, and then they take the third way. They take the values in the middle of the interval, right? Okay, and this is what they get. Okay, and then the exact value is in fact given by the integral. So the exact value of this green figure, so the exact area is given by the integral from 0 to 2 f of x dx, the integral as we defined just at the beginning, right? Now, of course, if you want to approximate it, you can make finer and finer partitions. And you can see that as you make them finer and finer, so you take more and more subintervals. So here they take 8 instead of 4. The values become closer and closer. And as you continue, you can see that the values are going to converge to the value of the integral, right? Okay, and so and here's another example. So in this example, the function is not monotone anymore. So what you can still do, choose, for example, points on the right or on the left or in the middle, right? And still you get some expressions. And then the exact area is going to be closely approximated by them. Okay. Okay, and then here, so you have a heuristic how from those considerations we arrive at the definition of integral. So we're not going to go into details here. So let me just say that basically what you do is, so as you take finer and so you have a function and you take finer and finer partitions, they will converge to a number. And this is the value of the integral. And furthermore, because the sum that you compute, so this is the sum, right? This is the sum of these are the areas of the rectangles, which are here, well, which you have here, right? And you can imagine that those rectangles approximate our function closer and closer, or approximate, I should say, the area, the figure under the plot. So they approximate this figure under the plot closer and closer, and therefore their area is going to converge. So, and this is, you see that the integral gives you an opportunity to compute the area. Okay, so we'll now let's also talk here. I mentioned, so I talked about the area, but so here the area is a little bit, this is true when we talk about non-negative functions, but if we're talking about arbitrary functions, which can also take negative values, then you should kind of think about the area as so the area which is above, the area which is above the axis comes with a positive sign, whereas the area which is below comes with a negative sign. Of course, the integral can be negative, as is, for example, here. Everything is below, right? And so, but of course, the area, kind of by definition, is positive, right? So, but somehow, so the integral is the difference between the area above the x-axis and below, right? So for example, in this example, so you have, this is part of the plot above. So this is, so okay, so here is the x-axis, right? So this one is x-axis. And so the area above it is here, right? And the area below is here. So you can see that the area below is larger. So the integral should be negative here in this case. Okay, so but now, okay, so that is all good and fine and interesting. But you can ask, so how to compute the integral? how do we compute it in practice? So it turns out that definite, so far, so this is a definite integral, and so far you you could listen to this and say, okay, so there is no relationship, no relation whatsoever between definite integrals and indefinite integrals. So the definite integrals, remember, so the definite integrals, those that we defined here and discussed in relation to the area, while indefinite integrals are the integrals that we discussed last time. You remember when you take when you find an antiderivative. Okay, so but here we come to the properties of definite integrals. Okay, so first of all, it is a linear, fundamentally a linear operation, right? And so I have such different properties. So if you interchange the limits of integration, it's going to be minus, right? So the sign is going to be minus. Now this comes from the definition. Okay, so this is just normally you want to have a smaller than b, because this is so how you want to have lower limits to be well smaller, right? And you want upper limit to be greater. But you can still define it in even if this is not the case, but then you can just use this formula to arrive at this example. Now, the second property is that integral from a to a of any function is 0, right? Well, and that makes sense when you think about the area. So if integral from a to a is going to be simply a line from 0 to f of a, right? And it has an area of 0 because every line, one-dimensional line, has 0 area. One-dimensional line has 0 area. Okay, so then you have multiplication by the constant, right? Okay, so this is also self-explanatory. It's a linear operation. And I think 4 is also clear. It's additive. Okay, 5 is a little bit more interesting. So if you have first thing, okay, you have interval a, b. So imagine a is smaller than b. And then you have a point c in between. So a is less or equal than c, less or equal than b. Then you can write it like this. And this is, of course, from the point of view of the area, this is kind of what you would expect. Because if you take two different figures, well, the area of their union is going to be the sum of their areas, right? So, okay, so this is totally expected. Okay, so I said that you can think of C as being in between A and B, but formally this equality in fact holds for any number of C, right? C doesn't need to be in between. Okay, so and then 6. So this is I think we also talked about this last time in relation to the indefinite integrals, that it doesn't matter what is your variable of integration, right? It's all the same. Okay. Okay, so let us see how the integrals can be computed. Okay, so we have this equality. So we're asked to find this integrals, given that this, so you know this and you want to find those integrals, right? So basically, you don't know yet how to compute the integrals, and we will talk about this in a moment. But you can reduce that integral to this integral, right? And remember, so I will recall also, I will repeat also the remark which was made last Monday, that typically you write here x squared plus 1 in parentheses, right? So you write here is the left parenthesis, and then, oh, come on. Okay, and then here you get the right parenthesis after the 1, right? Okay, so in this book, in this manuscript, they do not do it, but okay, so typically this is how it's done. So, all right, so this integral, you see, it's from 2 to 0. Okay, so from 2 to 0, and remember, you can swap the limits by adding minus in front. So 0 to 2, x squared plus 1, but the integral x squared plus 1 is given to us, right? And so we just know what it is. Now here we have 10, right? And here we just use the linearity. So we use it, so you can multiply by the constant and then put this constant outside, and this is what you get. And in this case, it's exactly the same interval as the given to us, because it's just a different variable, but the variable doesn't change anything, right? So you can think about, for example, in programming, if you take, for example, a sum from 1 to n, right? How you can take it? Okay, you're right. Okay, so you, for example, take s equals to 0, and then you say for I from 1 to n, s equals to s plus I, right? So this is how you would do it. Okay, one way to do it in programming. But then you could think it doesn't matter what variable you use. Doesn't matter what variable you use in the summation. You can say for I from 1 to n, or you can say for j from 1 to n, and so on, right? Of course, it cannot be n. For n from 1 to n, then you can get into troubles. Your program probably is going to is not going to produce the result that you intend. But if apart from variable n, which is taken, if you want to compute the sum from 1 to n, you can take any kind of variable, right? So it doesn't matter. And so you can think about those integration variables in the same way. So it doesn't matter in particular which variable you use, it's going to be the same result. Okay. Okay, so this integral, of course, would be very difficult to compute normally, but because the limits of integration are the same, 130, 130, it's going to be 0, all right? And okay, and so okay, so those examples we're going to skip. Of course, you can also consider them, but okay, let's say it's not too important, I think. Okay, so let's now make a small break. Okay, like 3 minutes. of the integral. Okay, so 7 is also quite clear if you think about it as you should think about it as this is just the area of the rectangle, right? Okay, 8 and 9 are hopefully also clear, right? So you have if the function is non-negative, then the integral is non-negative as well. And of course, if one function is larger than another, then the integral is also larger. Okay, then you have this estimate, right? Which of course 10 follows from 9. And then 11 also follows from 9 because f is less or equal than absolute value of f, right? So you take here to be the smaller function to be f and the larger function to be the absolute value of f, and this you get also this. Okay, so the main interpretation of the definite integral is the area under the curve, or rather not the areas per se, but you remember the difference between quote-unquote positive areas and negative areas. The negative areas is just the area under the x-axis, and positive area is the area above. Okay, and now we come to a theorem which is going to relate definite integrals, indefinite integrals, and the differentiation. Right. So you have so if f is continuous and g of x equals to this thing here, so the integral from a to x, f of t dt. So g is continuous and is differentiable, and its derivative equals to f. Right? So yeah, this is one of the most important theorems in probably in all of mathematics. So here we see relation between the derivative in definite integral, and remember that we had also the relation between indefinite integrals and the derivative, right? And so here you also have a continuation, right? So if f is continuous and capital F is an antiderivative. Antiderivative, remember, is just the integral which we discussed last time. Then you have also this. You have this equality, right? And so this part. So this is basically the same as the previous theorem. It's just formulated. Basically in the previous theorem, a capital F was G, right? But we didn't call it antiderivative. But here, in fact, this is antiderivative, and you have this property, right? So the integral of a from a to b f of x dx equals to this difference. So very simple. And then, of course, you can also say that the derivative of capital F is going to be small f. Okay, so and those results are fundamental for computing the definite integrals, because to compute a definite integral, you can compute the indefinite integral, and then and then you're done, right? Okay, so you can also just, okay, so let's first, before proceeding to computation of the integrals, let's consider this kind of problem that you have g of x equals to this integral. So g of x is a function of x, right? And x is here, I hope you can see it, on the in the upper limit of the integrals. X is in the upper limit of the integral. Right, and okay, so of course, this defines a function, right? As you vary x, you vary this expression. So this is a function. So okay, a function can also be defined in such a way. And then you can ask, so what is the derivative? And to find the derivative, you use this formula here. Right, so okay, the upper limit is x, and then you have some function under the integral. So, and the derivative of g is going to be just this function under the integral, but you substitute this variable, which is integration variable t in this case. You substitute t with x, right? And so this is going to be your derivative. Okay, and then you have example b. So here, in example B, you could, if it was kind of x here and some constant here, it would be the same. But here, what you need to do, you need to treat it as a superposition of functions, right? So you need to apply the chain rule, which we discussed about the derivative. We discussed a few lectures ago, a few weeks ago. Okay, so first of all, you can change the order. So you can put this variable to the upper thing here, because this is what you want to do, right? This is what you want to do because in this formula it is on the top. So you want the variable to be on the top. And then you use this formula with the change rule, right? Okay, so so we start from here. And then, okay, so u equals to x squared, right? And then you just proceed as follows, right? So you just du, so you apply the chain rule as was discussed. This is a chain rule, actually, also rewritten once again, right? And this is what you get. And so here you apply the fundamental theorem of calculus. So you have the variable in the upper limit. And then you have some expression here. So to find the derivative, you just substitute this variable u instead of t. And this is what you get. And then you here have the product du dx. So du equals to x squared. So du dx equals to 2x. And this is what you get. And then, of course, u equals to x squared. So you can just substitute, and this is what you get in the end. Okay, so you can also derive this general formula. And of course, you can also derive this formula for general kind of integrals, such kind of integrals, right? Okay, so this we're going to. Okay, and then, for example, this is an example, and you can just yeah, compute. You use this formula to compute the derivative, but okay, this is not very interesting. Okay, so now we come to computing of the definite integral. So, and of course, we use the second part of the fundamental theorem of calculus. So to compute an indefinite integral, it is kind of the easiest way, if it is possible, is to compute to compute a definite integral. The easiest way is to compute, if it is possible, is to compute the related indefinite integral, and then just use this formula. Now, I should say that there are cases when you can compute the definite integral, but you cannot compute the indefinite integral. But we will not deal with such cases in this course, right? So we don't need to worry about that. Okay, so let's go to this integral, which we discussed a little bit at the beginning already. So we remember the antiderivative, right? And so you use this, for example, as antiderivative, and this is what you get, right? Okay, so of course it doesn't, so antiderivative is not uniquely defined. You remember it's defined up to a constant, so you can add a constant. But of course, because here you have the difference, then it doesn't matter what constant you add, it's not going to change the outcome. Well, as you should expect, because of course this integral cannot be two different numbers, right? So it's just a single, it's a number, so of course it doesn't matter what constant you add. All right, and then so using this you can compute so you can compute the integrals. So let us consider examples. Okay, first in indefinite integral, we remember how to do it, right? So so this is just power, so polynomial, and for polynomial we remember how to do it. We just increase the power by 1 and then divide by this power. So here we divide by 3, 1/3, and here we divide by -1 and get minus in front. And then you have C, the constant. Okay, so here we just, so from the same function from 1 to 2. So we just use this formula and compute. So, okay, let me also say that no matter what integral, whether definite or indefinite integral you consider, this function under the integral is called integrand. So this is the integrand. So this is the function that is being integrated, right? In this case, it's y squared plus y to minus 2. Okay. Okay, so and this is, by the way, how you write it. So you have this integral, and then you say, okay, so this is the antiderivative, and then you draw this vertical line, and then you put the lower limit at the bottom and the upper limit at the top, right? So this is just how it's written, that you take the difference in two functions. Okay, and then you just substitute, so you substitute 2 right here. So it's going to be 2 to third minus 1 second, and then you substitute 1, right? And of course, take care of the signs, and this is what you get at the end. So okay, so the upper limit comes first, right? The upper limit comes first. And we need to be careful with the signs here. Very easy to make a mistake, because, for example, this term, you see this term comes with a minus, but you have also minus here. So you have two minuses, so in the end it is plus. And sometimes you may have more than two minuses, so then you have to keep track so that you compute everything properly. Okay. So this integral is interesting. If of course we could also just naively apply this formula, right? And we would get some number. But it is important. This is one thing which is very important, that to apply the fundamental theorem of calculus. Let's go back a little bit. We need f to be continuous. So we absolutely need function to be continuous. And what do we see here? Well, we see that this term, y2 minus 2, is not continuous at 0. So, in fact, we cannot apply the fundamental theorem of calculus here. So the function has to be continuous to apply the fundamental theorem of calculus. Okay, so you need to make sure that it is continuous. And then if it is continuous, then you can apply the fundamental theorem of calculus. And when you apply the fundamental theorem of calculus, then of course you try to keep track of all the signs and that you compute everything correctly. Okay, so let's make another break. So five minutes. Okay, so let us continue. So this is just the computation of integrals. So let us discuss one of those things and then compute another one ourselves. Okay, so you have the integral from -3 to 1 of this function. So you see that the function is continuous, right? So you just compute, and yeah, so I think it's pretty straightforward. Okay, so let's do the second one. So we have integral from 4 to 0. From 4 to 0, square root of t minus 2 dt. Square root of t minus 2 dt. Okay, so first thing we want to do is to have from 0 to 4, right? So you want the upper limit be greater than the lower limit. And then we open the parentheses here, so it's going to be t to the power 3 second minus 2t to the power 1/2 dt. Okay, so, and now we just take the and compute the antiderivative. So it's going to be what? It's going to be t to the power 5 second, but and then we divide by it, right? By the inverse of the power here, minus 2, and this is the same. So here we have power 1/2, so it's going to be t to 3 second. And here we divide by 2/3, right? So we divide by 3 seconds, so we multiply by 2/3, and then 2 remains, of course. And that's it, right? And then from 0 to 4. And also minus, not to forget minus, right? It's very important. Okay, so, and now we compute. now we compute. So it's going to be what here, minus. So 2/5 t to the power. So first I plug in 4, right? So 4 to the power 5 second. So 4 to the power 5. Okay, so 4 to the power 5 second. This is equals to 2 to the power 5, right? Because okay, you can write it like this: 2 to the power 2 times 5 second. So this is times, and this is of course 2 to the power 5. Okay. Okay, so 2 to the power 2 to 5 is 32, right? So it's going to be 32. A minus 4/3 times then 4 to power 3 second is going to be 8, right? By the same arguments, times 8. Okay, so that was the plus, rather the minus. So that was the upper limit. And then the lower limit is going to come with a plus, right? Because, okay, because, so this entire expression is with the minus. So normally the lower limit comes with the minus, but here it comes with the plus. Okay, and then we plug in 0, but in fact we see that 0, 0, so it's going to be just 0, right? So fortunately it's quite easy in this case. Okay, and then we need to compute this, so this is going to be 64/5 with minus, and then plus 32/3, right? Okay, so now we need to compute this. So this is going to be 192 minus 160/15, if I'm not mistaken, right? And this is going to be 32/15. Okay, so this is plus, this is minus, right? So this is minus. Okay, hopefully this is correct. Do you think, I mean, do you have some questions? If you have, write in the chat now. Okay, so let us see if this is correct. Yeah, so fortunately the answer is the same here, apparently, right? Okay, let's look at C. Okay, yeah. Okay, so we have here, so in this case, we also see that the function is continuous. By the way, of course, we should have said that, because, so we have this, so t minus 2 is defined everywhere, so that's fine. But then we have also square root, right? We have square root of t. But of course, we should say that it's fine to have square root of t for non-negative things, and here t is non-negative, right? So that's fine. Okay, and here we have w squared in the denominator, but that's fine because the interval is from 1 to 2. So the interval does not include 0, right? So that's fine. And then we just compute okay, so and this is d. So d is a little bit like a trig integral, so to say, right? So like a trig question. So so it's pretty simple, but you just need to remember that this is just 1 here, right? So this is 1 dr. I think we discussed it also last Monday about the indefinite integral. And here we talk about the definite integral. So this is just 1. And the antiderivative of 1 is just the function itself, right? So it's the identity function, right? So f of r equals to r. So you have here r, and this is your antiderivative, and this is what you get in the end. Okay, so basically, the computation of a definite integral very much comes down to the computation of the indefinite integral. Okay, so here are more examples. So in the first example, you have just a kind of sum of power functions, right? So and this is standard, very standard. So okay, so let's do this one. We have here right, so hope this is clear. Maybe I should save them. Okay, so so what was the integral? So we have the integral from 0 to pi over 3 to sine theta minus 5 cosine theta. D theta. Okay, so this one I think is also pretty straightforward. We just need to remember what are the antiderivatives of the trigonometric functions. So this is going to be, okay, so the antiderivative of sine is minus cosine, right? So it's going to be minus 2 cosine of theta. So the derivative of cosine is minus sine. So here you have no minus, so you need a minus here. Then we have minus 5. So the antiderivative of cosine is sine. Minus 5 sine of theta. And that's it. This is our antiderivative. And then the limits of integration here. Okay, and now we compute. So sine of pi over 3 is going to be what? It's going to be square root of 3 over 2, I believe, right? Sorry, it was cosine. It was cosine. So cosine of pi over 3 is going to be 1/2, I'm pretty sure. So it's going to be 1/2 minus 5 sine p over 3. So it's going to be 5 square root of 3 over 2 minus minus cosine of 0 is 1, right? And sine of 0 is, so it's 2 times 1, and sine of 0 is 0. Sine of 0 is 0, so minus 5 times 0, right? Okay, so we have here minus 1 minus 5 square root of 3 divided by 2. Here we have plus 2, right? And so we have, in the end, we have minus 5 square root of 3 over 2 plus 1, right? So just find the antiderivative and compute the integral. So I think pretty straightforward, and that's fine. So hope it was correct. Yeah. Okay, so here they warn about one thing that just a second. Okay. So here the authors talk about one thing that so when doing the evaluation at 0, you mustn't disregard f of 0 as 0, right? So you must still plug in, so as any other number, because in this case, okay, so this is what they get. So this is minus the function of 0. So this is, you have this in this parentheses, you have the function of 0. But it is not 0, right? It is in fact equals to minus 2. So you have minus 2, so you have plus 2. So it's important to do the evaluation properly. In here, they warn against it. So they call for care to be taken when computing the integrals. All right. Okay. This one is interesting. So okay, so but sec is 1 over. So this will meet. Or we can just do it as, so sec is 1 over cosine. So let's just do it like this. So pi, from pi over 6 to pi over 4, pi over 6, pi over 4, 5 minus a minus 1 over cos, so tangent of z divided by cosine of z, right? dz. Okay, let us do this. So first we rewrite tangent as sine divided by cosine. So what we get? Okay, so we get this integral with the same limits. 5 minus sine z divided by cosine squared z dz. Okay, so now we can put this 5 outside, right? So the integrals from pi over 6 to pi over 4, 5 dz minus the integrals with the same limits, sine z dz divided by cosine squared. Okay, so this one is pretty straightforward. This is just going to be 5 times pi over 4 minus pi over 6, which is going to be what? Okay, but I can also write 5z, this is the antiderivative, pi over 6, no, pi over 4 on the top, pi over 6 on the bottom. Okay, and here we have, so what about this integral? So how to compute this integral here? So imagine if it was an indefinite integral, how would you compute it if it had no limits? So we have here cosine, right? And here we have sine of z. Okay, so remember that cosine is 1 minus sine squared, right? So one way to compute it would be to do a change of variables. Okay, so the limits are the same. But here in the denominator, I have, I can just write it like this. So it's going to be minus differential of cosine of z, right? And in the denominator, I have cosine squared. Right? So I hope this is clear. So sine z dz equals to d cosine of z. Okay, so this expression is going to be, so this is z, by the way, this is not 2. Yeah, maybe it's better to write with this thing in the middle, right? I think it's in English they do it like this most of the time, at least in writing, because it would otherwise would be too easy to confuse with 2. I think it's not common in Polish, maybe, because I think it's a different letter, but okay, so here we have 5 times pi minus 4 minus pi over 6 is going to be pi over 24, so it's going to be 5 pi over 24. Sorry, over 12, right? Because yeah, 1/4 minus 1/6 is going to be what? It's going to be 1/12, right? Not 1, so it's going to be 2/24 and 1/12. Okay, and then we have this integral minus. Okay, the limits of integration are the same, but what is the antiderivative? The antiderivative is going to be simply 1 over cosine, right? So here we had, so first of all, this this minus, okay, so this minus, oops, and this minus, they kind of kill each other. So let's say we have here a plus. So we have here plus. And then if we take this integral, it's still going to be a minus, right? So if we just, so this minus we ignore, and this minus we ignore. But so dx over x squared, so the integral of dx, so the integral of dx over x squared equals to -1 over x, right? So we still have here -1 over cosine z, and then the limits are the same. So it's going to be p over 6 and p pi over 4. I should say pi, no, not p. Okay. And so this equals to also 5 pi divided by 12 plus, so cosine of pi over 4 is going to be a square root okay, so it comes with minus, so it's going to be square root of 2 over 2, and then 1 over that is going to be 2 over square root of 2. And then plus cosine of pi over 6 is going to be square root of 3 over 2, so it's going to be 2. So it's going to be like this. Okay, so this, of course, could be written just as square root of 2. Probably is better. And here is, of course, a square root of 3, right? Okay, so I hope this is clear, right? So here the difficult part is to separate kind of this integral and then to compute it, right? So do you have some questions or comments? So let's see, I hope this was correct. Okay, so apparently I missed 2 somewhere. Because here was 2, right? So here was 2. Okay, so I missed 2 at the beginning, so the computation was the same, right? So okay. Okay, so this is another example. So here, once again, you find the antiderivative and you are good. You are good to go. So find the antiderivative and then just substitute. And of course, okay, so this is something that you always need to keep in mind, right? Okay, and then one more example here. So this cannot be done, right? Because you have, so the division by 0, and then, so this is not continuous here. And by the way, so let me also say that, for example, if you have the integral from minus, or let's say from 11 to 24 dx, x minus 16, right? So this is not defined. This is not well defined because so the denominator turns to 0 if x equals to 16. And 16 lies between 11 and 24, right? So it doesn't need to be 1, or so it doesn't need to be only 0. So what I want to see is at the point where discontinuity, it can be any point, it depends on the function, really. Right. Okay, so then this is, you have piecewise, so piecewise defined function. So how to do integrals for piecewisely defined function? So you see that the discontinuity point is from 10 to 22. Sorry, is 1, right? So 1 is discontinuity point. So you cannot apply your theorem in this. But what you can do, first of all, the first interval does not involve this point. So the first interval is pretty easy, right? So if x is greater than 1, then f of x is just 6. So from 10 to 22 is just 6. So this is pretty easy, right? So you get just this, and this is all compute. Now here, the second interval does involve this 1 barrier. But what you can do, you can compute here from -2 to 1, right? So you compute integral from -2 to 1 of this, and then from 1 to 3 separately. And here the function is continuous. And then you can use those expressions which are given here. So from -2 to 1, you have 3x squared. And then from 1 to 3, you have 6. So, and then you just compute as a sum, and this is pretty straightforward. Okay, a little bit the same with the absolute value. So the absolute value, you use this representation for the absolute value, and then you do the same thing. Okay, so this we are more or less just skim through. Okay, so one way to compute the integral, the definite integral, without computing an indefinite integral, is to kind of get rid of odd or even functions, especially odd functions, but I think it's better to look at the example. Right, so okay, so for even function, you can of course just so for even function, you can say that, so if f is even, then the integral of -a to 0 f of x dx equals to the integral of 0 from 0 to a f of x dx. Now, we're not proving this properly, but so let's say so we have an even function. So this is a plot of an even function, right? And then we want to compute the integral, say, from -x to x here. Now, remember that the integral is the area below the plot, below the graph, right? So obviously, because it's even, it is symmetric with respect to this y-axis. with respect to this line, then the area of this part, right, is going to be equal to the area of this part of the right, to the right of the axis. So you can just say that the integral from minus x to x equals to 2 integrals from 0 to x, right? And so now, admittedly, it may not be too much of a simplification, but still I think it's nice. Okay, and here, so they use this formula for the first. So this is an even function, and so they just replace this integral from -2 to 2, and it should be -2 and 2. So it cannot be -3 and 2. Then you cannot already apply it anymore, right? And then you can do this. But this is more interesting for the even function, for the odd functions. Sorry, because for the odd functions, the integral is going to be in fact 0, right? So let's look at the odd function. Okay, so let's take this one. So where is the plot? Here is the plot. Okay, so oh, come on. No, it's in. Okay, so I will just try to draw it myself. So remember, the graph of the odd function is symmetric around zero, so it's focal symmetric. So the graph of even function is symmetric about with respect to the line y-axis, but for the odd function, it is symmetric around the 0. So, and then the integral. So, for example, you compute the integral. Okay, so let's say in this case from here to here, right? And so the plot, oops, the area of this thing here is going to be the same as the area of this, right? So the areas are this because this is symmetric, right? So I hope this is. So this is minus A, this is A. So the areas of red field figure is the same as the area of the green field figure because they're symmetric. But of course, they come with different signs. So hence integrals of, so odd, integral of minus A to A f of x dx is 0, right? And that's it. So in this example, for example, in this example here, it's just 0. Right? Okay, so and of course, so the limits of integrations are important here because you have, for example, if you replace here 10 with 9, you have a rather large number here. But still, it's nice if you have such symmetric things here and the function is odd, then you can just say, oh, it's 0. All right. All right, so let us now also discuss today the substitution rule for the definite integrals. So we're now going to take a break, a larger break a little bit. So I think 15 minutes is in order. And then we're going to discuss the substitution rule for the definite integrals. And then we're a little bit going to talk maybe about the organization, administrative stuff, and then we're just going to leave, right? So we're going to stop. But so first we'll have a break, and then we discuss the substitution rule, which is also a big topic and important, and basically, yeah, and then we discuss what we'll do in the future. Okay, so see you in 15 minutes. Okay. All right, so welcome back. So this is okay. This is not going to be absolutely the last thing that we discuss, but pretty close, I would say. So here, so we discussed the substitution rule for definite integrals. So let me say right off the bat that actually you don't need, strictly speaking, you don't need any of that for computation, because you can just compute the indefinite integral properly and then to plug in, right? So okay, so you have this integral. First of all, we need to make sure that this thing is well defined, right? That this is continuous and it is defined. So we have here square root, and square root is is defined for for non-negative arguments, right? But so we see t is from -2 to 0. So t cube is also going to be negative, but also it comes with minus, so it's going to be positive, and then +1, so it's going to be all positive. So that's fine. Okay, so if it was an indefinite integral, you hopefully already can figure out the substitution that would lead to the solution, right? T squared dt equals to dt cube, right? So the substitution is, the first substitution at least can be u equals to t cube, and then you would still have to do some other work. Okay, so and this is what they do here. Okay, they immediately take 1 minus 4 t cube, and then this is what they find by the substitution rule. Okay. Right. So okay. So this is a little bit not correct. What is written like here, because the problem is here that when you write it like this, so the second integral, right? You have du. So basically, you don't have any t anymore. But the limits of integration are for t. Right? The limits come from t. So this is very important. And you cannot simply do this evaluation and then compute the answer, because that would be wrong, right? So first, what you need to do, okay, so this is how you can do it, right? So you compute the integral, and so the integral, imagine the indefinite integral is going to be this thing here, -1/9 u to the power 3 where u is this, right? So it's a function of t. Okay, so you compute the indefinite integral, and then you write, you write, okay, so this equals to this, right? Because this is just, you compute the indefinite integral, no matter what methods you use. And then you plug in and you find the answer. Okay, and that's fine. And this is what you already can do, because you need to do one thing. So okay, so you're given this integral, right? And then you forget about the limits of integration and you compute the indefinite integral. You compute the indefinite integral and you find this expression here, -1/9 times this parenthesis to 3 right? And that's fine. And then you plug in your, so then you recall your limits of integration, and then you make them as the limits in the substitution, and then you compute, and that's fine. Now that was my method 1, and you don't need anything new for that one. So you should already be able to do it on your own, as it is as of now. But let's now have a look at the second method. Now, so you make the substitution, right? You make the substitution, you recompute du and dt, right? Okay, so, and that's fine, but you also recompute the limits of integration. So you also recompute the limits of integration. And this is how you can do it. So you change not only the variable, but also the limits, you see? And then this is correct. So if you had here 0 and -2, that would be wrong, right? But because, so you change the variable and you also change the limits of integration, then it's fine. Then this is legal and you can do it in computation. So for an indefinite integral, you just change the variable, right? Last Monday, in fact, we considered this step, okay, this line here. But today, so if you want to do it also for the definite integral, you also need to recompute the limits. And then, of course, the upper limits correspond to the upper value, the lower limits to the lower value. Okay, good luck with furniture shopping. Okay. Okay, so yeah, let me tell that we will finish actually, I think not too long from now, because so today we'll finish a bit earlier because well, okay, so this was it. So I have a difficult lecture for me tomorrow, which I need to prepare for. So okay, so that was about the limits of so that was, this is kind of what is new for the change of variables or substitution rule for definite integrals. Okay, so let's do this one, A. So the substitution, once again, we can determine. So if we take the derivative of this side inside, right, we'll find that the derivative is going to be 2 times this parenthesis. So this is our substitution candidate, and of course it's good. So and we'll find all this, and then we also change the limits, right? If w is -1 here, then u is also, so u of w is going to be -1 as well. And if w is 5, u is 35. And then this is your integral. Okay, so the author of the manuscript urges you not to get excited about different things. I don't know who will get excited, but okay, so yeah, sometimes, of course, the limits can, u of -1, if w is -1, then you also can sometimes get -1, so it just happens by, and then sometimes the numbers are large, especially if you work with the polynomials, right? So okay, so basically here is not much new, except that you have to recompute the limits, right? And so, okay. Okay, so okay, so this integral thing is standard, that you have, once again, the substitution, and yeah, it's fine, right? So in this integral, I think it's also straightforward because the substitution is just linear here. All right. So, okay, first of all, in this integral, you can split it into two because the e to the power y you can compute directly. You don't need a substitution. So you want to separate it. And then this one, you want substitution because so constant times y, you have the integral constant times y, so you want a substitution. Okay, and when you do substitution, once again, you recompute the integration limits, right? So 0 and 1/2 here, and here is going to be 0 and pi over 2. And then you just compute the integral and it's fine. Okay, so here we need more steps in this integral, right? So this is trigonometric integral. Okay, so first they split it into two. And in the first integral, they put the substitution of z over 2. And in the second integral, they take v equals to pi over z, right? So you have two different substitutions. Okay, for two different integrals, you have different substitutions. So nothing, well, nothing really special here is going on. And then for each of those, you once again recompute the limits, right? And then take care of everything. Okay, so okay, so this one probably, yeah. So this integral is not defined, right? Because okay, you have this division by 0 problem. Now, and let's consider this integral from 3 to 5. Okay. Okay, so let's. Okay, so the integral from 3 to 5 . 40 2 minus 8t squared dt. 42 minus 8 t squared dt. Okay, so the substitution here is going to be the denominator, right? So u equals to 2 minus 8 t squared. Yeah, by the way, I should of course also check that denominator does not turn to 0 on the interval from 3 to 5. But that's true because the zeros are going to be between -1 and 1, right? So because if t is like larger than 3, then this is going to be negative, and that's it, right? So it's not going to turn to 0. Okay, so this is our du. So du equals to -16 t. So 4t dt equals to 1/4 du, right? Minus. So minus important not to forget. Right, so I hope this is clear. And then the limits. So u of 3 equals to what? Okay, so 2 minus 8 times 9 is going to be -70, right? I hope that's correct. And then u of 5 is going to be what? 2 minus 8 times 25. And this is going to be 8 times, so it's going to be -100. 98, right? I hope that's correct. So the integral equals to, so for t dt equals to -1/4. I put -1/4 in front, du. Okay, du I put here. And then I have 1 over u. And then the limits from -70 to -198. Okay, so one remark here. So I wrote du first and then the function. And this is not conventional, but you can, but this is also okay. But okay, so you can do it, but it's usually it's not written like this. Okay, then we continue. Okay, so first of all, -198 is of course smaller than -70. So let's reverse the order and change sign, right? So we had minus here, so I remove the minus. And then here is going to be integral -198 to -70 du over u, right? Okay, and then, so this is just logarithm of absolute value, right? 1/4 logarithm of absolute value of u minus 198 minus 70. And so this is going to be -1/4 logarithm of 70 minus natural logarithm of 198. Okay, and we can simplify it a little bit further. Oh, so sorry, it's +1/4, right? Here it's plus, but here I can write minus because I change the signs here. Okay, so logarithm of 70, for example, is equals to logarithm of 2 plus logarithm of 35, right? So remember that. So let's say logarithm of 70 equals to logarithm of 2 plus logarithm of 5 plus logarithm of 7, right? Because 2 times 5 times 7 is going to be exactly 70, right? Okay, and the same here. So it's going to be logarithm of 39 is going to be logarithm of 2. Okay, so I will just write it like this: logarithm of 99 minus logarithm of 35. Okay, so do you have some questions about this example? About the substitution and the computations in general? Okay. Okay, so let's continue then. Right, so and this is also the answer that they get. Yeah, absolutely the same. Okay, so okay, these are a little bit more advanced examples. Okay, we'll discuss a few of them in a moment. And then I think we're going to just more or less complete well, then we're going to talk about some organizational stuff, including the homework. Yeah. Okay, so Okay, so you have this integral which looks quite scary, to be honest. So it's not clear what to do really in A. So let's see. Okay, so you take this as a substitute, right? And then of course it turns out that this is a fine substitute because you already have here. So we're somehow lucky. Okay, so this is your function u, and then you recompute, and you get also nice limits, right? And so this is what you get. This is what you get, and then you compute, and that's fine. It turns out to be quite simple, in fact. Here you take the logarithm, right? So the derivative of logarithm, remember, is 1 over t, and you already have 1 over t, so that's very convenient. And then the limits, the new limits are also very easy to compute because of how the limits are given here. Okay, so, and that's fine, right? So, and then it's straightforward. Okay, and here we have cosine of sine, right? So if we take sine as a new variable, its derivative is going to be cosine, which is also here. So this is very convenient. And this is all turns out to be just like this, right? So and again, here, don't get excited about this, right? So okay, and here we see that 2 over w, right? So 2 over w can be substituted, and the derivative is going to be something over w squared. So once again, and then we proceed in the usual manner. Okay, so that's it with the new material for today. So I will also send homework. I will send homework in a couple of days. So for today, I know you got a lot of homework, and not everybody, I think. So I'm not sure that everybody did it. I'll try to do it. So I would once again urge you to do it, and because it's important for your understanding of this material, and just for getting the practice. Once again, it's not really too difficult, but you just need to kind of get practice, and yeah. Okay, so and about the organizational stuff. So next week we are going to finish with the new material, and then we are going to do some repetitions. So we're going to just repeat. We're just going to be repeating stuff, and that's it. And then in 2 weeks we may have a test in 2 weeks, right? So on 18th of May. Now I say may have because there are 2 things. First of all, I still haven't thought about the platform to do it, but okay, there is still time. But the second is that so there have been some, as you may know, some gradual lifting of the restrictions. So today, for example, I went to the supermarket, and actually I found that some of the clothing shops were also open, and they have been closed since March. So it is possible that there will be some possibility to do the test of the exams offline, maybe later, but okay, maybe, who knows. So I will try to find out whether there are some instructions on this term, or whether it's okay for me just to do it online, and that's it. Okay, so today we finished a little bit earlier because, okay, as I said, yeah, I have still to prepare for tomorrow, which is a really difficult subject for me. So I have to prepare for it quite significant. I mean, and so okay. So if you have some questions, you can ask. You can ask now. And then otherwise, so I'm going to go off, and I'm going to, as usually, I'm going to keep the meeting going for 10 more minutes, in which you can ask a question. But if not, I'm going to end the meeting in about 10 minutes. Okay, so in case you won't have any questions, then bye for today. So see you next week. And yeah, bye.